Welcome back. Today we're going to be talking about how to determine when a rule is a function. Because in discrete functions, functions are often given as a rule in words, it may be difficult to determine if a given rule is actually a function. Here's what you need to check. First, you need to check that the rule applies to every element in the domain. Then, you need to determine when the rule is applied to an element in the domain, is the result of the rule in the codomain. And last, you need to determine if the rule is unambiguous. That is, there is exactly one output for every input. These are the three things that you need to check to verify that a function is well-defined. Let's see some examples of rules that break each of these properties. First property, the rule applies to every element in the domain. So here's an example. Let W be the set of words in the English language. Let L be the set of letters in the alphabet. Consider the rule, F, from W to L, that takes a word as an input and outputs the second letter in the word. Okay, this seems like it's reasonable. If you give the word dog, then the second letter in this word is O. But now let's think about whether this rule applies to every single word in the English language. A doesn't have a second letter. I doesn't have a second letter. What would F of A be? What would F of I be? The rule is not defined on those words, and therefore this rule is not a function, because it doesn't apply to every element in the domain. Let's talk about breaking the second property, which was, when applied to an element in the domain, the result of the rule lies in the codomain. So here's a rule from the set of integers to the set of integers. F of n is equal to n over 2. What happens when we take f of 10? Well, f of 10 is equal to 5. That's nice. What about f of negative 30? Oh, f of negative 30 is equal to negative 15. Great. But there are some elements in the domain which, when you try to apply the rule, do not output a value in the codomain. For example, f of 3, well, the rule says take the number, divide by 2, but f of 3 is equal to 3 over 2 is not in the codomain. So now let's talk about breaking the third property, that the rule is unambiguous. There's exactly one output for every input. Let's let n be the set of phone numbers in the world, and let's let p be the set of people in the world. We consider a rule that goes from the set of phone numbers to the set of people in the world that assigns to every phone number the person who answers the phone. So what's the problem here? Well, there are some phone numbers that when you call them, there are multiple people who answer the phone. So that would be like saying f of n is equal to person 1 and f of n is equal to person 2. But there can't be two outputs for one input. So let's do an example where we're given a rule and we need to determine whether it's a well-defined function. Let's let W be the set of all words, in quotation marks, made up of a sequence of 5 letters. So that's going to include all real words like brave and exits, but also made up words like QQZXJ. So now let's define a function, f from the set of these words to the set of these words, that takes every input, every word as an input that looks like W1, W2, W3, W4, W5, and gives as its output W5, W4, W3, W2, W1. Is this a well-defined function? Okay, so let's check each of the properties. Does this rule apply to all words? Given a word, it's possible to turn it around. Sure. Yes. We can apply the reverse operation to any word. Is the result of this operation in the codomain? Well, what's the codomain? It's the set of all words made up of a sequence of 5 letters. If we start off with a word with 5 letters and we turn it around, it still has 5 letters. So, yes, the reverse of a 5-letter word also has 5 letters. Okay, is it unambiguous? This rule is defined very precisely. There's not going to be 2 different answers for the same input. So, is this unambiguous? Yes. There is only one possible answer for every input. And so our conclusion, F is well defined. That's it for now. See you next time.